A compiled model artifact is not portable. It is a contract between your inference stack and one specific silicon target. When that target changes, a silicon revision, an MCU variant swap, an FPGA retarget, the contract is void. The industry called this progress. Measure what it costs your fleet update cycle before agreeing. The TF-Lite architecture was built on portable interpretation. A flat buffer serialized model graph, operators, weights, quantization parameters loaded at runtime by an interpreter that dispatched kernel implementations through a delegate registration system. ARM Cortex CPU, GPU via OpenCL or Metal, Hexagon DSP, 1, TF-Lite file, hardware variation absorbed at the delegate layer. Deployment meant shipping one artifact. Hardware heterogeneity was a runtime concern, handled by registered delegates, not baked into the artifact itself. The cost was latency, interpreter dispatch overhead, unoptimized memory access patterns, missed opportunities for operator fusion. For many edge programs, that cost was acceptable. The TF-Lite was operationally cheap in ways that mattered on a fielded fleet, one file, updated once, running across multiple hardware generations. The migration to compiled graph runtimes, XLA, Apache TVM, MLIR lowered artifacts, Core ML compiled models, delivered what inference benchmarks demanded: throughput, operator fusion, target-specific intrinsic selection for Neon SVE2 or Hexagon HVX, elimination of interpreter dispatch overhead. A model compiled against a Cortex M55 target profile runs materially faster than interpreted. That is not the flaw. The flaw is the scope of what the benchmark omits. The compiled artifact is now bound to that exact hardware target. Deploy it to a different MCU family, or to the same MCU after a silicon revision that altered SRAM banking or the DSP pipeline, and you do not have a slower model. You have an incompatible artifact. The failure mode is not performance degradation. It is silent incompatibility, a model that initializes but faults or produces wrong outputs on silicon the compiler did not target. That failure surfaces at integration, not at design. Consider a fielded sensor network, 400 embedded inference nodes, hardware procurement locked to 2 MCU families on a 36-month production run. Midway through, the primary MCU vendor spins a silicon revision, updated SRAM topology, revised DSP pipeline. The compiled artifacts, optimized for prior rev memory characteristics, fault at initialization on the new silicon. The update path is not a model push. It is full recompile, reprofiling on new silicon, revalidation of outputs, and for any safety-adjacent system, recertification against a toolchain that has itself likely incremented versions since original compilation. That is not a software update event. That is a re-engineering event masquerading as one. The architectural correction is compilation tiering. Separate the canonical model artifact, an MLIR or ONNX intermediate representation with full quantization metadata and operator constraints, from the target-specific compiled binary generated at deployment time. The canonical IR is the asset under version control, under cryptographic signing, under certification. The compiled binary is ephemeral, generated at first boot via a secured on-device or edge-proximate compilation service, then cached to write-protected flash. When silicon changes, you update the canonical IR and reissue. Target-specific compilation happens automatically against the new hardware profile. This mirrors LLVM's separation of intermediate representation from machine code, applied to neural graph compilation. The canonical artifact is hardware agnostic not because it ignores hardware constraints, but because hardware adaptation is deferred to a defined, auditable compilation step. One constraint to approved toolchain versions, logged, and independently verifiable. This fix is not free. First inference latency on cold boot increases by compilation time, on a Cortex M55 at 400 MHz, that is seconds for a non-trivial compute graph. The device needs sufficient flash and SRAM headroom to host both the canonical IR and the compiler runtime, which is a real constraint on Class 1 embedded targets. The compiler toolchain now becomes a certification surface. Under DO 178C or equivalent rigor, it requires qualification evidence. And if compilation is edge proximate rather than on-device, you have introduced a link dependency that must survive comms degradation. None of these are disqualifying. All of them must be priced into the architecture before you commit to the approach. The compiled graph runtime solved inference latency. It did not solve fleet management. The canonical model artifact belongs under version control, versioned and signed. The compiled form belongs at the target, generated on demand. Conflating those two artifacts is how benchmark culture becomes logistics debt, and why your third hardware revision will be the one that surfaces it.